Hi everyone, I'm Leila. I'm a graduate student at Grenoble Alpes. This project is completely unrelated to my graduate work. I'm working on it with Gabriel Toubi from Nantes. A few of you will have seen me talk about this at LPSC, but I do appreciate the opportunity to talk about it again to a more targeted audience and hopefully get ideas on how to improve the model. So the model is a model for the evolution of Pluto's core, which is generalizable to other bodies, and includes the evolution of compaction over time and how that affects the water-rock interactions that are possible. Since I am pretty much the first person to bring up Pluto at this workshop for mostly my terrestrial colleagues, just here's a small reminder of what Pluto is. It's the largest trans-Neptunian object. It's very far. It's very cold. It's very probably differentiated more or less in this manner. So with a rocky core and a water ice crust. Also Charon, which is its biggest moon and which quite probably formed via giant impact with the Pluto precursor, and that is quite possibly why they are both differentiated. A big question for Pluto is whether we have a liquid ocean under the ice crust, which has persisted till now, which can potentially be maintained by, is the mic close enough? Everybody can hear? Yeah. Which could potentially be maintained by radiogenic heating, then tidal forces, although those will be pretty much negligible by now, and the chemical water-rock interactions that we've heard about a lot earlier today. So just again, the big question is how the core evolves, how it interacts with the mantle, and can the processes that are implied in all of that sustain the liquid ocean for 4.6 billion years. I'm sure it will come as a great surprise that other people have already created models for the evolution of the interior of icy bodies. Including Gabriel Toubi himself with co-authors who developed a model for Titan and Europa, which has a simple 1D core model, which just has heat diffusion and I think no other evolving parameters, and a parametrized convection 1D model for the ice mantle, which uses scaling laws. Then Robuchon and Nimmo developed a more complicated mantle convection model, which actually has explicit convection in 3D. And applied it to Pluto, but the core model was very simple. Then Travis, with co-authors, applied something like this to Europa and Enceladus, and actually included this time a core mantle interaction in the form of hydrothermal circulation in the porous layer of the core. And Marc Neveu also did this, also included this as a parameter in his model for Ceres, and parametrizing it as a thermal conductivity. Both of these last models, however, just took a static porosity for the core and didn't take into account how it might evolve over time, so from differentiation up until now. So what I'm aiming to do here is to model exactly that and how that's going to affect the hydrothermal interaction. So the core model is partially based on Gabriel Toubi's pre-existing model. So it's parameterized in one dimension. The heat transfer is described as conductive. Then there is a silicate viscosity that depends on temperature with empirical values based on wet and dry olivine depending on the temperature. The complication there is that we don't have good empirical values for cold silicates, so I've arbitrarily set off a maximum viscosity, which I vary within this small range, because the literature values on that are quite different. The compaction is described with a complicated viscoelastoplastic model developed by Yarshin and Pedlachkov, which I will describe in just a minute. Then the hydrothermal convection is also, as Marc Neveu did, parameterized as an equivalent heat conduction and integrated into this heat transfer equation. All of this is coupled with the same 1D model that Toubi et al. Used, which has a stagnant conductive lid and is mostly controlled by the ammonia concentration. This is just to see how the heat how the heat evolution of the core affects the ocean, to see if that's going to be something that we can have or not. So there's a lot of parameters to vary there. I've chosen a set of nominal parameters that are not necessarily the most realistic, that not necessarily the ones that have the most realistic options. What they are is more or less the middle of the range for everything that I've varied, so we can see how varying them in either direction affects the result. So first there is the rheology, which is actually used for the yield strength in the compaction model, so we'll see that later. And the initial porosity, the grain size of the silicate, the silicate thresholds, and the ammonia concentration. The core compaction model is a model that describes the evolution, the compaction, so the evolution of porosity over time, as a function of the effective pressure, which depends on the solid and fluid pressure, which I took to be lithostatic and hydrostatic respectively, and the porosity. And also this effective viscosity, which is calculated dependent on the compaction regime, which can be viscoelastic, and then a transitional viscoplastic regime, which is where you have plastic compaction around the pore and viscoelastic elsewhere, and then full plastic compaction, which has no time dependence. And the boundaries between these are going to depend on the effective pressure and also the empirical yield strength, for which we're using the stuff-like parameters. I have lots more slides detailing all of this further. If anybody wants to see them, I'm happy to show them, but I don't think I have time to develop all of it now. So this is what I get for the nominal case, for which I gave you the parameters. We have like plots like in depth and in time. So we have the inner. We start with a uniformly porous core. So in this case, it's 20%. The inner core compacts quite rapidly, but then we have gradual compaction for the outer layer, and we do maintain a porous layer pretty much up until now. We can see that with our parameter that describes the convection, we can see that we have convection in this layer, and that the heat is evacuated from the outer layer. This is just how the compaction occurs, the regime that I described. The viscosity is pretty much stuck at the arbitrary threshold that we set, except in the middle where the temperature gets high. And here we have the dehydration. This is the dehydration threshold I set for the olivine, and then it also, again, is stuck at the threshold. So this is pretty much controlled by the arbitrary parameter that I set. Here, just to take a look at how it varies with parameters, here is the different outputs we get from varying the initial porosity. So first, the heat output generally peaks in the first around 1 billion, well, 0.5, 1 billion years. It's at around 150 gigawatts. The core temperature varies a little bit with the initial porosity. It peaks at around 1,000 Kelvin and more or less stays there. And here we can see that we have this rapid compaction and then a thin porous outer layer that remains. Also, with the grain size is actually implicated in the description of the it's implicated in the permeability, and the permeability affects the convection and so the equivalent convection. So this controls the temperature and the heat output very strongly. You can see that for larger grains we have a much stronger heat output, and the core is cooled much more efficiently. Not so much the thickness of the porous layer that's unaffected. And this arbitrary viscosity threshold that we set also is a very strong control on the heat and the porous layer, but not so much the heat output, because this doesn't affect the heat evacuation by convection so much. And the yield strength that we choose also has a slight effect, but is something that's quite an arbitrary decision in the first place. So it can be taken as an average of that. So just as a summary, we have a rapid compaction. We have an outer porous layer that remains more or less there for the entire duration. We have a strong control by this arbitrary silicate threshold. Then we have a strong effect of grain size on the heat flux and core temperature, and also an effect of the rheology we choose on the heat flux and the temperature. Now, when we screw this onto our mantle model, we see that we have generally a liquid ocean that starts as a pretty thin layer, then thickens rapidly, and we have this bump that goes up to about a billion years, and then thins out again, but remains there more or less until the present day. And then we have this convecting layer that also thins out over time with a growing conducting lid. And this is how it varies with porosity. So like it's a bit thicker, but it still more or less ends up at the same thickness. For the grain size, also the beginning thickness is strongly affected, but we still get more or less the same result at the end. Also the same for the silicate threshold. We can see that we have some variation in like what happens over time, but the end result in the present days is more or less the same for all cases. Weird color, but same for the rheology. The one thing that strongly controls the mantle state as of now is the one mantle parameter that we're varying, which is the initial ammonia concentration. So when we set it to 0.1%, the ocean actually does disappear at around 3.2, I think, billion years. But if it's higher than that, then the ocean does remain at varying thickness until the present day. And because Bill McKinnon asked me last time, when we don't have any ammonia, then it freezes at about 1.2, I think, billion years in. There you go. So that's just a quick summary of everything I just said. So most things only affect the ocean depth in the early few billion years and doesn't persist until the current day. The only thing that does is the initial ammonia concentration. So what the other thing that matters, I guess, is the time that we run the simulation for, because we don't really have a timeline for this impact event that formed all of this. So that's the other thing it's going to depend on is when we set the timeline. Just as a curiosity, this model is generalizable, so I also ran it for Karen. So we have also the decreasing porosity, and but which is much more gradual because, well, it's a much smaller body and there's less gravity. And so we have this nice, smooth, viscoelastic compaction with a pretty cold core. And yeah, just this more or less same dependence on the parameters. The heat output is, yeah, about 5 times less than that for Pluto. And yeah, that is not enough to sustain an ocean, and even actually to have an ocean in the beginning. We can't, the model actually doesn't run because it's, yeah, it doesn't manage even in the time steps that I have it set to. So this, well, this doesn't mean that Karen never had an ocean. I think it's a paper by Alyssa Roden that suggests that tidal heating is sufficient to have one in the very beginning of its evolution, and that forms, and that may form tilted tectonic features. And I'm not sure where the analysis of the New Horizons data is with that. But that is the other significant heat source that we can have for Karen. It is tidal dissipation and tidal heating, and since radiogenic heat output is clearly not enough, we have to, I think, come back to that and see if we can have an early ocean on Karen with just tidal heating. Just to conclude, the core model is a realistic model that includes compaction, which hasn't been done yet so far. So it hopefully will be useful for other researchers, including those working on other bodies, because the model is easily usable for everything else. Specifically for Pluto, we get a liquid ocean that persists more or less until the present day with almost all the different model parameters that I tried. On Karen, we don't have that. Which isn't really surprising. So we do need to look at other heat sources that can make that happen. And we do have some poor constraints, which is the rheology and the maximal silicate threshold, and those need to be looked at, and probably empirical lab work needs to be done there. We can also hook up the core model to an explicit 3D convection model for the mantle and see what happens spatially also there, and see how that may correspond to spatial features that we see. So, and yeah, the tidal forces for both Pluto and current. Right. Sorry. So the tidal forces also need to be included in this for both Pluto and current to see how that compares to the radiogenic heating and what the effect will be. So I think that's everything. I'll take any questions. Thank you. Great.
Thank you very much, Leila. Questions about this model?
I have a question. Do you have since these are maybe trans-Neptunian objects, as you suggested, do you have a sense of how large of a sort of a third body you could input into the system that would add heat to the system but not overly disrupt to the present configuration that we see?
Well, I don't do very much work with orbital dynamics personally, so I can't really tell you that. I mean, you can put as big a body you like, really, and just see how it works. Not really my specialization.
It's neat. Let me ask you a question. So, in your porosity evolution model, in the beginning, these pores are all filled with water.
Yes, they are.
What happens to that water as
it goes up?
So it's
evacuated into the mantle. That's it's the permeability that governs how. Well, actually, it's
your porosity.
A complicated thing in it's part of the compaction model, I think. Just a sec. How did I define that? One sec. Just taking a look. Right. Well, we are assuming that we're just assuming that the pores are connected and that they're just. I mean, the compaction is basically as like the speed that is being evacuated with upwards. Just like the fluid, the fluid's being evacuated into the mantle, and that allows for pore collapse.
Okay.
Is there room in this for localization of shear? I mean, you have this viscoplastic and these viscous responses. I thought Laurent Montesi was playing around with some localization, not on these planetary bodies, but do you understand? So
I understand, but I mean, it is a pretty parametrized model in 1D, so I'm not sure how you can localize it as it is, but I suppose you could attach it to local 3D models. I'm sure that's possible. Yeah, just see how the parameters interact.
All right, great. Thanks for the questions. Thank you for a great presentation, and please join me in thanking all the speakers for this afternoon session.